All right, guys, here we go. So I had mentioned cofunction identities are actually in 6.1 from your textbook, but the rest of these are from 6.2 and 6.3. So that's why this worksheet is called section 6.2 and 6.3 derivations. And the first set of identities that we're going to talk about are the cofunction identities. Okay. And the cofunction identities are kind of cool because it has to do with why the trig functions are named what they're named, right? Cofunction, there's a cosine, cosecant, cotangent. Okay, we'll talk more about that in a second. But for deriving our cofunction identities, refer to the triangle below and fill in the ratios for the different angles, alpha and beta. So this is a right triangle, meaning we can use our handy dandy SOHCAHTOA. Oops. To fill in those ratios. So if you guys want to go through and fill in the ratios, let's do it. Sine of alpha, well, opposite over hypotenuse, that would be A over C, right? Cosine of alpha would be adjacent over hypotenuse, so B over C. Secant of alpha, that's the reciprocal of cosine, so C over B. Cosecant of alpha would be the reciprocal of sine, so that would be C over A. And then tangent is opposite over adjacent, so A over B, meaning cotangent would be B over A. And then for the angle beta, opposite over hypotenuse would be B over C. Cosine of beta, adjacent over hypotenuse would be A over C. Secant of beta would be the reciprocal of cosine, so C over A. Cosecant of beta would be the reciprocal of sine, so C over B. Tangent of beta would be opposite over adjacent, so B over A. And cotangent of beta would be the reciprocal A over B. Does anyone have any questions about any of those, how I got any of those ratios? Can you guys check my work and make sure they are all true? And then the question that I have below, what do you notice about the ratios? Which are the same? Well, look, we have an A over C here and an A over C here. We have a B over C and a B over C. C over B, C over B. Try to use different colors. C over A, C over A. A over B, A over B. And color would be different enough. This one B over A. Yeah, that looks different enough, right? B over A. My husband's colorblind. He wouldn't be able to tell the difference, but I think for the rest of us, that works. So with the two different angles, we have some ratios that are the same, right? Each angle has a ratio that matches the other angle. So we're able to say that sine of alpha is equal to cosine of beta. Cosine of alpha is equal to sine of beta. Secant of alpha is equal to cosecant of beta. cosecant of alpha is equal to secant of beta. Tangent of alpha is equal to tangent of beta. And tangent of beta is equal to cotangent of alpha.
Wait, would it be cotangent of beta? Or is it?
Thank you for catching that. Yes. Thank you, Ryan. So then if we look to the cofunction theorem, the cofunction theorem says a trigonometric function of an angle is always equal to the cofunction of the complement angle. And remember, complementary angles are angles that sum to 90 degrees, or in radians, that would be pi over 2. So we noticed, this is kind of the simplified list that I did above, right? That sine of alpha equals cosine beta, secant equals cosecant beta, secant of alpha equals cosecant of beta, tangent of alpha equals to cotangent of beta, right? And it's in the name, sine, cosine, secant, cosecant, tangent, cotangent, for which are cofunctions of each other, right? That's where the names come. It has nothing to do with reciprocals. I know whenever we first start talking about the trig functions, everyone's like, well, wait, shouldn't the reciprocal of sine be secant because it starts with an S, and the reciprocal of cosine be cosecant? But no, that's not what that has to do with. The naming has to do with them being cofunctions. So if we take that relationship between the two angles that are complementary, right? If we have alpha plus beta equals to pi over 2, and we solve for beta, right? We would have pi over 2 minus alpha. And if we think about replacing each of these betas, then bam, we have our cofunction identities, right? Sine alpha equals to cosine of pi over 2 minus alpha. Right, that came from up here. Secant alpha equals to cosecant of pi over 2 minus alpha. Those guys. Tangent alpha equals to cotangent of pi over 2 minus alpha. So those are our cofunction identities. Cofunction identities don't really come up so much in the fun verifying identities. They could. Somebody could make one to practice. But like knowing cofunction identities might come up in different derivations, like other derivations or different places in calculus. So you need to know them. You got to memorize them. Or I'll put a little memorize. All right, does anyone have any questions for me on the cofunction identity? So that whole process we just did, referencing the right triangle, that was to derive our cofunction identities. And if it's okay with you guys, we're going to move on. Okay. The sum and difference identities, the first one is not fun to derive. It's pretty complicated, but we're going to do it. We can do it. And then the other ones, we needed the cofunction identity, like we're about to use the cofunction identity to help us with deriving some of these other ones. So there's the cosine, sine, and tangent. You can see I have a different page for each one. There's the cosine, sine, and tangent angle, sum, and difference identities. I say angle because I feel like sum and difference identities, they're known as the sum and difference identities, but whenever I think of it, it's because it's the angle sum. Like that's the helpful part to me. And we're going to start with the cosine, sum, and difference identities. And I've drawn a picture for you guys. And if we look at this first picture, and we think about being in the unit circle, both these pictures are the unit circle. So that means that this point right here would be 1, 0. I have the angle beta, right, in red here. The angle beta. And the point on the unit circle that corresponds to the angle beta is cosine beta, sine beta. And then I have an angle in quadrant 2 that I'm calling alpha. So the point on the unit circle that corresponds to the angle alpha is cosine alpha, sine alpha. And if we were to subtract the angle beta from the angle alpha, that would give us this angle here that I have in green that we can call the angle alpha minus beta. It's the angle alpha in standard form minus the angle beta in standard form. That angle is alpha minus beta. And I drew a line connecting the point cosine alpha, sine alpha, and cosine beta, sine beta. And I'm going to call the distance between those 2 points d sub 1. Does anyone have any questions about that picture? You're probably like, what the heck is going on? Why are we doing this? But even if you're having those thoughts, does what I have labeled in this picture make sense?
Yeah.
Thank you. Thanks for the thumbs up, Oscar. Okay, so I want you to think about taking that angle alpha minus beta and rotating it so that it's in standard position. That's what this picture is. So that the point that corresponds to the angle that's in standard position, right? Meaning that it starts on the positive x-axis and rotates in the counterclockwise direction. So that the point that lies on the unit circle is cosine of alpha minus beta, because that's the angle name. Like that's what I've named it. I haven't named it anything else because I came up with it from taking alpha and subtracting beta, comma sine alpha minus beta. And this point, since we are in the unit circle, is 1, 0. The distance between the 2 points that are on the unit circle hasn't changed, but I'm going to call that distance 2, d sub 2. And you guys can see from the 2 pictures, even if my picture is slightly off, but theoretically, d sub 1 and d sub 2 should be equal to each other, right? So I just want to remind you of distance formula, right? That should find the distance between 2 points in the XY plane. Distance formula is the square root of the change in the x coordinates. So x sub 1 minus x sub 2 squared plus the change in the y coordinates squared. That's just distance formula. So referencing distance formula, we're going to come up with what d sub 1 is and what d sub 2 is. James Duong, you have a question.
Yeah, can you explain quickly what standard position means again?
Yes, if an angle is in standard position, it means that its initial side is on the positive x-axis. So like you can think of the angle as starting at the positive x-axis and then rotating either in the counterclockwise direction or the clockwise direction. Counterclockwise direction gives us a positive angle. And then it terminates somewhere else in the XY plane. So I moved the angle alpha minus beta, right? Alpha minus beta is the angle name. I thought about rotating that angle or picking it up and placing it into standard position in the second picture so that its initial side is on the positive x-axis and then it terminates in quadrant 1. Good question. Did that answer your question?
Yeah, it did.
Cool. So I'm going to come up with 2 statements. So the statement for d sub 1, so distance 1, and the statement for d sub 2, distance 2, using distance formula. So d sub 1 would be the square root, the change in x coordinates, right? So that would be cosine beta minus cosine alpha squared plus the change in the y coordinates, sine beta minus sine alpha squared. Right? That's referencing the first picture. That's the distance between these 2 points. And then d sub 2, referencing the second picture, be the change in the x coordinate. So that would actually be 1 minus cosine alpha minus beta all squared plus change in the y coordinates, which would be 0 minus sine of alpha minus beta all squared. And the reason that I did this is we've already said, like proof by picture, d sub 1 is equal to d sub 2. So by setting these 2 distances equal to each other, we are going to derive the cosine difference identity. So I'm going to take that first, so d sub 1, which is cosine beta minus cosine alpha squared plus sine beta minus sine alpha equals to d sub 2. And I am not expecting you to do this derivation on your own. This is the honors class. You should be interested in where are these formulas, these identities that I'm telling you about that you have to memorize. You should be interested in where they're coming from. Okay. Do we all understand how I got this statement? How we got here from those two pictures? Okay.
I understand, but like, how does the left picture relate to the right picture? Like how?
It's how I came up with the angle alpha minus beta.
Okay. Okay.
Does that make sense? Like we were able to come up with the angle alpha minus beta from taking the angle alpha and thinking about subtracting that angle beta.
Okay.
It's really taking an angle from quadrant 2, subtracting an angle from quadrant 1.
All right.
Okay. Your angles might look slightly different than mine, and that's okay. It's just in theory, they're the same. Okay, so what we're going to think about doing next is squaring both sides of the equation. This is actually an identity, and we're basically going to manipulate it to get to our fundamental identity for cosine difference. So if we think about squaring both sides, well, then we're just left with cosine beta minus cosine alpha squared plus sine beta minus sine alpha squared equals 1 minus cosine alpha minus beta squared. And then since that's 0 minus sine of alpha minus beta, I can actually just write that as sine squared of alpha minus beta. All right, from here, the algebra is tedious. We're going to multiply all of these squares out. We're going to multiply this guy out first. And we would get cosine squared beta minus 2 cosine alpha cosine beta plus cosine squared alpha. And then when we go to multiply out the sine of beta minus sine of alpha squared, we'll have plus sine squared beta minus 2 sine alpha sine beta plus sine squared alpha. I'm going to move this over a little bit. And then on the right-hand side, when I multiply out 1 minus cosine of alpha minus beta, that's going to end up being 1 minus 2 cosine of alpha minus beta plus cosine squared of alpha minus beta plus sine squared of alpha minus beta. I'm running out of room. So all I did was multiply all those squares out. From here, we can simplify this really yucky looking statement using our handy dandy Pythagorean identities. Because we have cosine squared beta plus sine squared beta, that's going to be 1. And then we also have cosine squared alpha plus sine squared alpha. That would also simplify to 1. So then that gives us 2, right? Because 1 plus 1 is 2, minus 2 cosine alpha cosine beta minus 2 sine alpha sine beta. And then on the right-hand side, not quite as obvious just because the angle name, but cosine squared of alpha minus beta plus sine squared of alpha minus beta, well, that's 1. And then we already have the 1 there, so that ends up being 2 minus 2 cosine of alpha minus beta. And if we thought about subtracting 2 from each side, well, bam, bam, that's gone. And on the left-hand side, I'm going to factor out a negative 2. I should say I have a little rhyme to help you guys with memorizing this set of identities too, once we finish. And then if we think about dividing by negative 2 on each side, those can cancel. So that we're left with just cosine alpha cosine beta plus sine alpha sine beta equals to cosine of alpha minus beta. You guys, that is the difference identity. We usually have it memorized as flipped around. So cosine of alpha minus beta equals cosine alpha cosine beta plus sine alpha sine beta. And then to derive, do I want to give myself an extra piece of paper? I could probably do it in this space. So that's the cosine difference identity. To get the sum identity, which would be cosine of alpha plus beta, you can think about the fact that cosine of alpha plus beta can actually be written as a difference, right? It can be written as cosine of alpha minus negative beta. Where then if we were to replace all of the betas in our angle difference identity with negative beta, right? We would have cosine alpha, cosine negative beta plus sine alpha times sine negative beta. And then simplify using even odd identities. Well, cosine of negative beta would just be cosine of beta. Sine of negative beta would be negative sine of beta because sine is odd. So we could change this to be minus sine alpha sine beta. And there's our angle sum identity, our cosine sum identity. So cosine of alpha plus beta is equal to cosine alpha cosine beta minus sine alpha sine beta. And it's becoming clear to me that it would be pushing it to try and get through this entire worksheet today. Thank you for hanging in there so far, guys. Okay, so we have, this is the cosine, we've just derived the cosine sum difference identities. Well, we did difference first and then we did sum. Does anyone have any questions so far? I'm thinking that we will do the sine sum and difference identities, which are much easier to derive. And then we'll stop. And we'll finish next time. Does that sound okay to everyone?
Yeah.
Okay, thank you. Okay. So for the sine sum and difference identities, remember the cofunction identity that sine of alpha is equal to cosine of alpha, cosine of pi over 2 minus alpha? Well, that would mean that sine of alpha plus beta is equal to cosine of pi over 2 minus alpha plus beta, right? That's just applying the cofunction identity. And if we thought about distributing that negative, we would have cosine of pi over 2 minus alpha minus beta, which by the associative property of addition, we are allowed to regroup the pi over 2 minus alpha. Right? That's by the associative property of addition. You can reassociate. Remember back in Algebra 1 when you're like, why do I need to know what the names of these different properties are? Well, here they are. Okay, so then now we can think of this as our first angle, this as our second angle, and apply the difference identity for cosine, which is cosine of the first angle times cosine of the second angle plus sine of the first angle times sine of the second angle. And again, using cofunction identities, we're going to replace the cosine of pi over 2 minus alpha and sine of pi over 2 minus alpha. This would be sine of alpha times cosine beta plus cosine of alpha times sine of beta. And that is our angle sum identity. That sine of alpha plus beta is equal to sine alpha cosine beta plus cosine alpha sine beta. So that's the sum identity for sine. And then super easy, to derive the difference identity, right? So alpha minus beta can be written as alpha plus negative beta. So applying that identity we just derived, sine alpha times cosine of negative beta plus cosine alpha times sine of negative beta, and then use the even odd identities to simplify. So that's just sine alpha cosine beta minus cosine alpha sine beta. And you guys, I know this has been a lot, so I'm gonna stop there and we'll pick back up with the tangent sum and difference identities on Wednesday. But does anyone have any questions for me before I let you guys go? So the only thing I want you to work on